For this video, I just want to do a short recap and review of some of the key points that I've been talking about in the last couple of videos. Remember that the key goal, or the main goal of our Chapter 7 in the Sandler textbook, is being able to model phase equilibrium for situations in which we don't have comprehensive data. When comprehensive data is not available, how can we model phase equilibrium? And the applications for this are vast, right? So chemical engineers need to know at what conditions we have phase equilibrium occurring, because so many processes in chemical engineering industry involve vapor-liquid equilibrium. So separations, for instance, any type of storage operation where you are storing a chemical at a certain temperature or pressure. Maybe you have a vapor chemical and you want to compress it and condense it into a liquid such that it takes up way less space and it's less expensive and easier to handle. So the main idea here is that we started with our equilibrium criterion. So Gibbs energy of vapor and liquid phases, or I'll generalize here. So it could be vapor solid phases or liquid solid phases. For phases in equilibrium are equal. Remember that the magnitude of Gibbs free energy is dependent on the reference state. So Gibbs free energy can take on any magnitude of value. And if you're looking up Gibbs free energy in a table or something, always be cognizant of the fact that it's calculated relative to some reference state. So that allowed us to say that Gibbs energy of phase 1, I think this is what Sandler's notation does. He likes to put Roman numerals for the phases. This is what it says in math terms. And then we did a couple of practice problems. Or before we did practice problems, I talked about two ways that you could do a shortcut. So talked about equations like the Clapeyron equation. And then we simplified that to the Clausius-Clapeyron equation. Remember, Clapeyron is not really usable, but Clausius-Clapeyron is all in terms of stuff that we know or should know. And also empirical methods like the Antoine's equation. And then in a couple of practice problems, I showed you how that would look. So in the two practice problems that we did in the last couple times, both times we wanted to calculate the vapor pressure of a certain substance. I'm sorry, the saturation pressure of a substance at a certain temperature given some amount of information. This is a problem that we did in Excel, where we had a reference Gibbs free energy. And remember, the solution procedure here was to start with the definition of the differential form of Gibbs free energy, which is V dP minus S dt. And for this particular problem, and then the other problem that we did, we said that temperature was constant because we have one temperature defined at 300 K. And pressure is not, so pressure is constant for the phase change part of the operation. But the reason why we're not canceling this dP here is because we do have information about the Gibbs free energy of the substance at the reference state. And we don't know what pressure is going to be the equilibrium condition. So we have to have a change of pressure in order to go from the reference state to the conditions where we have phase equilibrium. So we're left with just this part of the equation, and we did this twice. So we did the liquid side and the solid side. For the liquid side, the key assumption that we made was that V underbar is constant, which is very reasonable for a liquid, which allowed us to pull this out of the integral. So when we integrate this expression, we got that Gibbs energy at equilibrium. So we'll call it G sat for liquid. I'm trying to think what the notation is. Let's do that. So Gibbs saturation at the liquid is equal to Gibbs at the reference state. Let's put a subscript. Gibbs reference plus, what was it here? This was linear, so we pulled V out of the integral, integrated from P1 to P2, and said V under bar of P saturation minus P of the reference state. All right, so this equation, in order to solve this equation, we had to know what the Gibbs energy of the reference state was, which we have. We have it set to 0 in the liquid phase. We needed to know the pressure at which that reference state was set. We'd have that. That was 1 bar. And we also need to know the molar volume of the liquid. And that was given in the problem statement as well. So with these 3 things known, we have we have 2 unknowns, but we have an equation that will say that the Gibbs energy of the vapor is equal to the Gibbs energy of the liquid. And that was one of the pieces that allowed us to solve for P-sat. That was one side. Remember, on the vapor side, I'll go a little bit further. For the vapor side, we could not pull the V under bar out of the integral, and said we had to assume that it was ideal, which was reasonable at this low pressure, but you can imagine how it would be more complicated at a higher pressure. And we said that V was equal to RT over P. And the equation here was that Gibbs saturated for the vapor phase was equal to Gibbs at the reference state. However, we couldn't, remember, we don't use 0 here. Or no, we did use 0 here. No, I'm sorry. This problem, we had what the Gibbs energy of the vapor phase was at our conditions. So at the conditions, I'll just call that G1 plus, this was RT ln of P saturated over P1. And again, here we had what G1 was. This was that number. We have R, gas constant, we have T, and we have P1. So we put these 2 things together. We say that Gibbs at saturation for the liquid is equal to Gibbs saturation for the vapor, and we solve for saturation pressure. And this was an okay solution, but the problem with this solution is that the vapor phase was very sensitive to P changes, and the liquid phase was not sensitive at all to pressure changes. Therefore, there was nothing wrong with the solution that we did if we carried it out with a high degree of precision. But this is a new plot, so in that Excel file, I just replotted this quickly. Let me blow it up a little. So this is a plot of, on the y-axis, I've got the Gibbs energy difference from the liquid and vapor phases, and this was in the units of the problem. And on the x-axis, I have the pressure in bar. Therefore, the pressure in bar at which there is no difference between the liquid and the vapor phase will be our saturation pressure, P-sat. Of course, by looking at this plot, and I've scaled it appropriately such that I can compare it to the solution from the next problem, is that the line looks almost vertical. Of course, how vertical the line looks is a function of how you plot it. But the point is, for a very small change in pressure, I get potentially a very large change in the difference in Gibbs free energy. The other problem here is that, say I have a difference in Gibbs free energy of 150 bar centimeters cubed per mole. That is a very hard number to contextualize. I don't know if 150 bar centimeters cubed per mole is large, small, in between. It really makes it very difficult to get an intuitive feel for things. So with that motivation, I told you about fugacity, and then I solved a different practice problem for the fugacity. So this is a different problem that has the same type of general idea. I want to model the vapor-liquid equilibrium for a refrigerant that is used in air conditioners. So I wanted to calculate the vapor pressure at 15 Fahrenheit. So different problem, different units, different magnitude of numbers, but same general idea that at a certain temperature, I want to calculate what the vapor pressure is, given a little bit of information. So here, instead of using Gibbs free energy as the equilibrium criteria, I use the other equilibrium criteria, which is that the fugacity of the liquid phase has to equal the fugacity of the vapor phase. Remember all the details about the mathematical definitions of fugacity, and I can get to the point where I can say this by starting with Gibbs free energy for the phases must be equal, so therefore the fugacities must be equal as well. And then with a couple of other derivations, we had this final equation where we said that the ln of phi was equal to z minus 1, where z is the compressibility, minus ln of z plus the integral as v goes to infinity to v of 1 minus z over v times dv. And this is an equation that will allow us to calculate the fugacity for the different phases. So you think of this equation that I just wrote as being analogous to this dg equals vdp. We just have to evaluate this expression in order to find the fugacity of the liquid and vapor phases, and that will allow us to say that these are the conditions that must be met to have equilibrium. So in order to evaluate this expression, you need to have an equation of state, and that is because it involves z and integrating with respect to v. So for the van der Waals equation of state, I think I showed you all the steps involved with this, but we got down to the expression. So it's ln of f over p is equal to z minus 1 minus ln of z plus ln v over v minus b minus a over vrt. So remember, all I'm doing here is I'm using the form of the van der Waals equation that is in terms of z. I substituted that equation in for that z, divided through by v, and then I integrated with respect to v. And so this chunk gives me this stuff. All right, but it's the same equation. And then I plug in all my numbers, or I calculate everything. That will allow me to calculate what my fugacity is. So same equation for the liquid and the vapor phases. The only difference is, what was the difference between the two phases? The difference between the two phases was the molar volumes, which I had to calculate. Remember, those are not given in the problem. I had to calculate what the molar volumes of the liquid and the vapor phases were by solving the van der Waals equation of state. And I did this in a guess and check manner. So for many different pressures, I solved the cubic equation of state. This is where I use solver in Excel to get the molar volume of the liquid and the molar volume of the vapor. Then I solved this equation. Then I set the fugacities equal. So it's a little bit more involved of a procedure. But that allowed me to solve the equation the same way. So all I'm doing is I'm finding the pressure at which I have equal fugacities. So this is the plot that I was talking about that is going to compare with the other one. So let me put them side by side. Oops. All right, so on the right-hand side, I've got the same plot for the different problem. The only difference is I'm plotting the fugacity difference now between the liquid and the vapor phases. I tried to scale the plots such that they were comparable, and the different pressure units made that a little bit more challenging. So over on the right-hand side, I've got a difference of 10 psi, which is a little bit less than 1 atmosphere, 1 bar. Remember, 14.7 psi is 1 atmosphere, approximately 1 bar. So this interval from 100 to 110 psi maps to about 0.66 bar, which is about the same scale that I have. And notice now that my fugacity is much closer to between the two phases. So if I have a small error, right, I don't remember what the exact answer was. I think it was 105.2 or something psi. Now, if I move that pressure by a little bit, so even if I'm at 104 psi, I'm still going to be pretty close. My fugacities are going to be relatively easy. That allows us to more quickly identify the correct solution. So it's not that one is more correct than the other one. It's just that using fugacity is a little bit more convenient and reproducible to use. The other benefit of using fugacity is that fugacity has units of pressure. So I can plot the fugacity coefficient, which is fugacity divided by pressure. And I did that over here to get an idea for how well we have ideal behavior. So remember, for a fugacity coefficient of 1, this is phi. for phi is equal to 1, we have ideal behavior. And we should see that happening at low pressures. So this plot shows that as pressure increases, my fugacity coefficient is decreasing, and that is getting me further and further away from ideal behavior. This gives us a better idea for a number. So if I have a fugacity coefficient of 0.8, that is immediately more recognizable to say, like, okay, I'm pretty far away from ideal gas behavior, but perhaps not as far as some other conditions. I want to give you the form of this equation, but for the Pang-Robinson equation of state. So this one would be a pretty long derivation for Pang-Robinson equation of state. So same procedure here. I'm solving the Pang-Robinson equation of state for Z, plugging that expression of Z in for there, dividing through by V underbar, and then integrating with respect to V underbar. This one is a little bit more complicated as well. I'm going to need some more space. So don't worry about the derivation for this one. It's pretty lengthy. ln of phi is equal to same start Z minus 1 minus ln of Z minus B. This is a capital B. I'll define that in a moment. Minus A over 2B square root of 2. This is the equation. So notice it's got these two parameters here, capital A and capital B. Don't get those confused with lowercase a and lowercase b, which are the parameters that are used in a lot of these cubic equations of state. This capital A and capital B are substitutions that were made to make the equation look a little bit neater. So this is a habit of thermodynamicists of always, you want your final equation to look pretty and not be too intimidating, although oftentimes it is quite intimidating anyway. But they do all these substitutions such that there's parallel structure between the formulas. But the capital A is written for you there, and the capital B is written for you here. So notice that the lowercase a and the lowercase b are coming into play in the capital A and capital B. But in order to solve this, you'd have to plug all this stuff in, and then the procedure is the exact same. So you calculate what the fugacity of the liquid is, calculate what the fugacity of the vapor is, set them equal. The pressure at which that happens is the solution to the problem. A couple more things I want to point out before I wrap this video up. The cool part about these methods is that you can calculate fugacity for situations that don't physically exist. So in the Excel examples that I did, I was calculating the fugacity of, let me try to remember, what was the answer here? We calculated that the vapor pressure was 105.2 psi A. All right, so above that pressure, we are going to have a liquid. Above P equals liquid. And below that pressure, we are going to have a vapor. However, there was nothing stopping me from calculating the fugacity of the liquid phase at a pressure of 30 psi, for instance. And there was nothing stopping me from calculating the fugacity of the vapor phase at a higher pressure. You may think, well, why would I want to do that? That's not a physical solution, or it's not a physically relevant thing that I'd want to do. But remember, we're going to start dealing with mixtures. So ask yourself, we know that the boiling point of water is 100 degrees Celsius. Yet, when we go outside in Gainesville, when the temperature is far below 100 degrees Celsius, and we feel that humidity, we are painfully aware of the water vapor that is in the air. So why is it that water vapor can exist at conditions that are below what the boiling point of water is at 1 atmosphere? And that is because it's the partial pressure of water vapor that is relevant. It's not the total pressure. So because the water vapor makes up such a small percentage of the air, the pressure is much lower. So having a mathematical explanation for what the fugacity of a pure liquid phase at pressures that are far below what the actual pressure is going to prove very helpful in the future. And then the other thing that's cool about this equation that I wanted to point out is that it's the same exact equation that we're using to solve for vapor and liquid phases. So we start with any form of this equation. We can solve the same thing for vapor and for liquid, and that is helpful as well. And that is why most of these models are very useful for doing these calculations. So that is all for this video. See you next time.